Let's figure it out. Okay, cool. We are rolling now. So we talked about last time very briefly that we find the area of a triangle using half. So A as an area. Let's not use that because that's a confusing variable. Area of a triangle equals half of BC sine A, right? So any of the sides can be BC as long as A is the other way. And do you know what I mean when I'm like using these small and big letters? So
like angle versus sine.
Like B, C, A. I'll just go over it quickly.
Okay.
So basic notation on when we are labeling a triangle is that whatever letters you use for the angles are going to be in capital letters. And then all the sides directly opposite to that angle is the same letter except lowercase. So this would be A, this would be C. So basically this is saying that this is half of whatever side 1, side 2, times sine of the angle in between them.
So sides are lowercase?
Sides are lowercase, angles are uppercase. So this area formula is basically saying area of a triangle is the length of two sides times sine of the area, sine of the angle between them, divided by 2. And notice that this this formula is not just right triangles. It can be any triangle whatsoever. So this one kind of looks equilateral, so you can use it for any triangle. It does not have to be a right triangle. Okay, and we went over the derivation last time, but if you really need to see that, then go back to the last video. Okay, so two really, really important laws that we're going to learn about today. The first one is the law of sines, and we can derive that from the area equation. So if we say so you can take any two sides and the angle between them. So this is going to be the same thing as half of AB sine C, which is the same thing as half AC sine B, right? So if we divide these two by half B, well, okay. Let's divide both of them by ABC, by half ABC, okay? Divide everything by half ABC, okay? What we notice is that BC and BC cancel out, these halves cancel out. AB and AB cancel out, and the halves cancel out. And AC and AC cancel out. And what we are left with is sine of A over A equals sine of B over B equals sine of C over C. So this is called the law of sines, law of sines. And this is going to be really, really, really useful in solving a triangle. And by solving a triangle, I mean oftentimes questions will ask you to find the angle measures of all the angles and the side lengths of all the sides in a triangle. And so if you know sine A, if you know, you use law of sines when the information you're given is angle side side, angle side, and there's lots of angle side angle. Essentially what this means is if you're given an angle and then two consecutive sides, or you're given an angle, and the next side, or an angle, the next side, and the next angle, then you can use this to solve the rest of the triangle. You can find whatever it is. You can find. So let's do some practice with this. So this is 30, 45. Gee, I'm trying to make up a practice problem, and I'm not sure it works. Okay, let's make this 2, 3. And I guess we'll see what happens. I'm not sure entirely this is a valid triangle, but we'll try it. Okay, so essentially how you would do this. Oh, actually I can't do that. Angle, yeah, okay, angle side. Cool, cool. So, oh wait. No. Oh, actually this one's fine. This one's fine. I lied. Okay, so how we would do this is that basically this law of sines thing is saying that sine of some angle divided by the length of the side opposite to it is some ratio for any side and angle that you choose. So sine of this over this is going to be equal to sine of this over this, which is equal to sine of this over that.
Okay.
Okay, so notice that we have one pair of an angle on the opposite side, and that's 30 and 2. So we can use this to solve for everything else, pretty much. So what we're going to do is we're going to say sine of 30 over 2 is equal to sine of 45 over some length that we're trying to find. You can call it b, whatever you want to call it. Okay, and then pretty much just solve for b. You can use a calculator in this case, because most of the time the angles are not going to be nice angles. So you're probably going to end up with a decimal, which is fine.
So you do that, and you just do the same thing for the last one?
Yes, or what you can do for the last one is, since you have neither, you don't have this length, and you also don't have this angle measure, notice that, what's the total angle measure inside a triangle?
180.
Yeah, so you can just subtract these two from 180 and find out. Okay, so let me know what you get.
You got like a negative number.
You should not get a negative number. What are you putting in?
Sine 45 times 2 over sine 30.
Yeah, it should be something positive. Are you using radians instead of degrees?
How would I know? Is there like a calculator function?
Yeah, your calculator is set to one of the two modes. I'm not really sure how to see it on yours specifically, but I can get you. What was your answer?
It was like negative 1.722.
Yeah, that's not right. This one. Yeah, this one is set to degrees.
Okay.
And this was my bad. I'm supposed to put degree signs. This is actually like an error that you can be marked down for, but I always forget to do that. So yeah, if it's degrees, you have to put the degree sign. Because now that we're working radians, might get wonky. So what was your answer? Okay.
Okay, I get a positive.
So what was your answer? 2.83. Exactly. Okay, so now we know that this side B, which is directly opposite of the 45, is going to be 2.8, right?
Okay.
And so now you can subtract 75 from 180, and what's this angle measure get? This is very not drawn to scale diagram, but what should this angle measure be?
180 minus 75. Sorry, I'm really bad at mental math.
That's okay.
105.
Yeah, okay, so this is 105. Right, so now you do exactly the same thing.
Oh, yeah.
Instead of 45, just give me sine of 105 over So you're solving for C.
Identity 3.86.
3.86.
Yeah, try.
Wow, this triangle was actually a real triangle. I just completely made up numbers and I was like, I hope it is. But yes, it worked. Okay, so a way that you can check your answer is I'm not sure if you already know this, but the smallest angle should correspond to the smallest side. The largest angle should correspond to the largest side. Okay, so if I redraw this more accurately, it would probably look something like this. This would be 105. This would be 30, 45. So yes, this makes sense because that's the largest one, that's the smallest one. And yep, it works. Okay, so trying to think of how to make this not complicated.
Well, I think this wasn't that bad.
It's about to get bad.
Yeah, I guess so.
Okay, so when you're given this case, angle side side, this means you're given an angle, the length of one side on that angle, and another side, the side right after it. And so if I draw a picture, I don't know how long this side is going to be, but I know that I have some angle here. And I know the length of the leg. Okay, so I don't know where it's going to be or whatever. But I don't know this angle here, so that's why I drew so many of them, because you can imagine that's like it rotates around. So the issue with when you're given this information is that, let's say this is the height. Okay, this is the height of our triangle. So the length of the side, the other side could be here, it could be wherever, right? So if the next side that you're given over here, if this side is greater than A, let's call this side A, then there's only one case and it has to be over here, okay? Because there's no other way to make a triangle besides that. If the length of this side is less than your height, then you can't make any triangle at all, because just imagine like a really short thing dangling there. It's never going to reach the bottom, right? If it's shorter than the height. The problem comes when you have something that's in between these two lengths. So if you have something, let's say A is 5, say A is 5, and the height is 3. What if the leg, let's call this B, let's call this B. What if leg B was 4? You have two options. Either it can go out here, and this could be 4, or you could go in here and make your triangle an obtuse triangle. You don't know which one, so that means you have to solve for both. So when this happens, angle side side, you have to check to make sure that you have to solve for both triangles. Now sometimes the second triangle that you solve for doesn't make any sense, like what I told you before, the longest side should correspond to the biggest angle. Sometimes it won't work, but most of the time you'll end up with two triangles. So when you have this case, what you can do is, I always like to do the acute triangle first, so the one outside of the height. So you have this angle measure. I'll put this in green. So all the stuff that you're given is going to be in green. Have this angle measure. You have A and you have B. So using this information, you can find this angle here, right? You can find A using law of sines, right? If we have this pair and we can do that. And then you can solve the rest of your triangle by subtracting whatever
But
from
don't
180.
you need to know the height to solve that triangle?
No, you do not.
Why?
You do not. You just use law of sines. Because sine of b over b is going to be sine of
Oh,
the
well,
sine of value
yeah, I
of
mean,
a.
you said that I have two.
I see. You can if you want to check your answer, but really all you should need to know is that when you're given this information, this sort of thing is a possibility.
How do I get my second answer for the second try?
I'm about to tell you in a minute.
Oh.
Cool. Getting ahead of myself. So that's fine. So we understand how we can solve this triangle, right? So then we can draw our second triangle. The second possibility is if b is over here, right? So our triangle would look like this. Yeah. So once again, we're given A, B, and angle B right here. So what you need to know is, so if you look at this black triangle on the outside, the first one, when you use law of sines, your calculator is usually going to give you an acute angle, and that's going to be this one when you evaluate. So this would be sine. These work. If you were to solve this black triangle, you would have to do sine b over b equals sine a over a, and then you have to solve for a, right? So in order to just isolate this variable inside the sine, you'd have to do sine inverse of something, right, to find a. And remember what we said yesterday about the range of sine inverse is always between negative 90 degrees and 90 degrees, right? We're looking at this half of the circle. So this means that your answer here is always going to be between 0 and 90 degrees.
Okay.
It's always going to give you the acute angle out here, okay? And so in order to find what this angle is, this one right here is supplementary to A. You should probably write this down. The obtuse angle in your second triangle is supplementary to the acute angle in the first one. When you have this ambiguous case, it's called the ambiguous case because it's very ambiguous. Okay?
So the obtuse angle?
Yeah.
Will be supplementary
to that one. And you can prove that if you want, but I'm not going to go into that because then we have to.
It will be supplementary to that.
To A, yes. So if you are solving for A here, you're given this stuff, and you're solving for this angle, it's going to give you some acute angle. But the issue is you might have a second possible triangle where this is obtuse. And to find that, you would do 180 minus A. Supplementary means they add up to 180 degrees, right? So
then you just use supplementary.
Yes, then you would use this one, this angle, because this angle up here, you don't know what that is either. And so that depends on what this one is. So after you've found this supplementary angle, then you can solve your second triangle and subtract 180 from, like, you'd add these two and subtract it from 180 to find this missing angle, and then find your missing step. Okay. Since we are short on time, I'm not going to go into this very much. I'm not sure if there is one of these on your final. There might be though, I'm not sure. But I didn't give you one on your homework because this is the only time this thing is complicated because this is really simple until you get to here, right? So I didn't give you one of these on your homework, but if you feel you need practice with it, because I'm not sure if it's on your final, I would just go look up ambiguous case and law of sines, and you'll come up with tons of this stuff. Okay, then we have to move on.
Yep.
Next law is called the law of cosines. And once again, law of cosines, just like law of sines, is for all kinds of triangles, not necessarily right triangles. So law of cosines. Can you see it? I hope you can. I can't, and what a bummer. This is equal to c squared equals a squared plus b squared minus 2ab cosine c. Okay. All right, so notice that this part looks like the Pythagorean theorem, right? So this is kind of just, you can think of it as like an adjustment for anything that's not a right triangle. If this was a right triangle, and we made c equal to 90 degrees, because let's make little c equal to hypotenuse. And the big C, that would be 90 degrees, right? What's cosine of 90 degrees? You can look at your unit circle. You do 90 degrees here. What's the x coordinate?
0.
Exactly. So this would make this entire term 0. So for a right triangle, that's a special case of the law of cosines, where this part equals 0. This part would equal 0 from Pythagorean's theorem. That's just a little derivation thing.
So for right triangles, that section would always be 0.
Right. For a right triangle, it's this law of cosines just becomes the Pythagorean theorem. But in most cases, you're not going to have a right triangle. So I'm not really sure what to tell you about this besides that you use it for when you're given SAS and SSS. If you're given some random triangle, let's say you're given SAS, so you're given this side, this angle, and this side. You can't use law of sines because you don't have a pair already, right? So you'd have to use law of cosines. Law of cosines is useful because you don't have to have this pair. You can just plug in, let's make this A, B, and angle C, and then you can find your missing side. Okay, and same thing if you have SSS, and you're given all three sides. Once again, you don't have an angle and side pair to use, so you just plug in numbers and you find whatever angle you're looking for. Okay?
So you can do this with SAS and SSS?
Yes.
But what about like ASA, like
For
ASS?
Okay, so for ASA, only using law of sines is sufficient in order to get your answer. Because this is a lot more complicated equation, you should just use law of sines.
Oh, okay.
And for some of these cases, you might not even have enough information to do law of cosines. But law of cosines you use when you cannot use law of sines, which is for these two cases. Yeah.
So the whole point of all these laws is just to solve the triangle.
Solve the triangles, exactly. And there's a lot of word problems involved in this. I'm sure there are some in your homework. I didn't make homework every day, so I don't know. But in the future, there's going to be tons and tons of word problems related to this. Like, for example, there's a map. Like, there's a person here, and a person there, and a person there, and we like have to find whatever. Yeah, tons of word problems. But that's the general concept. It's pretty much just plug and chug. And yeah, that's it.
Okay. Cool. What about like tangent?
Tangent? Well, you don't need tangent for law of sines, law of cosines. Tangent you really only use with right triangles because you have to have opposite and adjacent. And if you don't have a right triangle, it's hard to define what opposite and adjacent are. So, okay. We're on time. Do you want to take a break or? Cool. Actually, we should keep going for a little since we started late. Let's keep going for just a little bit and then,
Yeah, sure.
Yeah.
Whatever works.
You can eat while we do this anyway, so get more food if you want. Okay, so right now we're going to go over some identities in trig. And by identities, I just mean they're just some equations that help you to simplify things or evaluate things. But we should already be familiar with the reciprocals. So basically sine, cosine, tangent, these are already simplified. You can't do whatever to them. They're already like as simple as they can be. Tangent, we should already know, is sine over cosine. Right, sine theta over cosine theta. Cotangent equals, can you tell me what cotangent theta equals?
Cotangent theta, the reciprocal, so sine over sine theta over cosine theta to the -1.
So like this, right?
Yeah.
Which is equal to cosine over sine.
Yeah, sure.
Yeah. Okay. This is kind of the answer I said before. And this, I'm not sure when you would use this. Well, you sometimes would use this if you're like, say you're given something where everything is in tangent except there's like one cotangent, then you can say cotangent is the same thing as 1 over tangent theta. And this might come in useful, I don't know. Sometimes it's useful if you have to convert this back to tangent, but yeah, so you should know that cotangent theta is equal to that, and it's also equal to that. And tangent is equal to that, okay? And what do we know about cosecant theta? Man, I cannot write. Cosecant theta equals, in terms of sine and cosine.
Cosecant theta. Wait, and that's also just the reciprocal, right?
Reciprocal of which one?
Cosine.
No. So remember the one with a co goes with the one without a co? So cosecant has a co in front, so it goes with sine.
Sine.
Okay, so this is the reciprocal of sine. Okay, and secant theta is reciprocal of, what do you think?
Cosine.
Cosine. So you guys should have all this stuff memorized. It should just come naturally, but I put it on your little cheat sheet thing. It should be the first thing on there, in case you forget. So I think we're going to allow you guys to use these sheets during your final.
Okay.
Yeah, so it should be right there on your sheet. Okay, so we should already know this stuff. Okay. Oh, another thing we kind of did not go over. Did Jimmy go over odd and even functions? No? Okay, I'm going to introduce a new term. Let's say you have a function that looks like, I'm kind of going to branch away from trig for a little bit to introduce this new concept. So notice that this graph is symmetrical across this axis, the y-axis, right? So something that is symmetrical across this axis, we're going to call an even function. Even function. Okay? And a function
symmetrical across the x-axis.
The y-axis, yes. And we call this an even function if f of x is equal to f of negative x. Okay, that makes sense, right? Because if you go some amount here, okay, that's over there, and if you go the same amount negative this way, it should be the same number, right? So it's even when this negative, when negative x is the same as x. And let's say we have another function. Let's use something before. You see this?
Yeah.
Okay. Let's say it looks like this. So, great, that one doesn't work. And I have to be drawing these for the rest of my life. Okay. Cool. So, in this graph, I want you to notice that if I go some amount this way, let's say I go 3 out this way, it'll be some number. And if I go out 3 the other direction, it's going to be the negative of this number. So basically what this is called is reflecting it across the origin. So So that means f of negative x equals negative f of x.
F of negative x equals negative f of x.
Right. So if f of x, let's say this was x and this was f of x, right here, this point, that means if you go all the way to negative x, your result should be negative this, negative f of x. Okay? So when we're looking at sine and cosine,
Great question.
Mhm.
So is that f of negative, the second one, is that for odd functions?
yes,
or-
it's odd.
Okay.
Okay, so when we're looking at sine, sine looks like this. Okay? Sine, we're going to say, I think it's kind of difficult to see on this graph. It's easier if I just draw this part. If we just draw one cycle. Does this look like an odd or even function?
An odd function.
Exactly. So, because sine is odd, that means that sine of negative x
Equals.
is the same thing as negative sine of x.
So then why does it say f of negative x is equal to f of x?
Negative f, there's a negative here. I didn't draw it very clearly, sorry.
Yeah, it's okay.
Okay. Now, if we look at cosine, cosine looks like this thing in red. Is this odd or even?
Even.
Perfect. So cosine is even, which means that cosine of negative x equals cosine x. You're not going to use this way too much, but it's very good to do this for like solving equations and things. And also it'll be helpful for deriving the next couple steps.
So are these the identities?
They're not really identities. Well, identities aren't like a black and white thing. Identities are just whatever, like this equals to that, then you can call it an identity, I
I
suppose.
see.
But it's just a useful thing to know about trig. Think of it that way. Okay. Okay. So next we have Pythagorean identities, and for this we're going to look at the unit circle again. Well, these work. Wow. Okay, so we know on the unit circle that r is 1, right? So this is going to be 1. The radius is 1, right? And do we remember that x equals r cosine theta and y equals r sine theta? Remember this? Okay, so since r is 1, we can just get rid of that. So basically the coordinates here are cosine theta, sine theta. Right? So if we were to simplify, or not simplify, but put this right here. And right here, this would be sine theta. Right? That means the length of this side is equal to sine theta. And the length of this side is equal to cosine theta. Right?
Yes.
So if we draw a triangle if we use the Pythagorean theorem with this triangle, a squared plus b squared equals c squared, right? So sine squared theta equals, plus cosine squared theta equals 1. This is your first Pythagorean identity. And from this one, you can pretty much derive everything else. So this is really important.
So you can use this to solve the triangle essentially?
This is not for solving triangles, it's just, we'll see how it's used a little bit later, but I first want to introduce them all to you, and then we'll do some practice. So Notice sine squared theta. This is just common notation. Essentially what this means is sine theta squared. That's what sine squared theta. And the reason why they write it like that is because people are too lazy to draw parentheses, so they just put the square there. Because you can't just do that. If you have that, then this would be sine of theta squared, and that's not what you're trying to do. So that's why they just put the square over there. That's all that means. So the next Pythagorean identities. So let's start with this one. If we decide to divide everything by sine, actually let's divide everything by cosine first. So if we divide this by cosine, divide that by cosine, or cosine squared theta, sorry, sine squared. Then we're going to get, what's sine over cosine?
Sine over cosine? What do you mean?
What does that simplify to?
Sine over cosine?
No, so what did we say tangent was?
Oh. So
tangent is sine over
tangent is
cosine,
sine
right?
over cosine.
Yeah, so this would be sine squared theta over cosine squared theta would be tangent squared theta, right? Tangent squared theta, cosine squared over cosine squared is 1, so plus 1 equals, and what's 1 over cosine? What does that simplify to?
Secant.
Secant. Right, so this is secant squared. Secant squared theta. Okay, this is your second identity.
And do these identities have like labels or just like identity?
They're just, no, they don't have an order, but this is just the order in which I'm writing them.
Okay.
They don't
so
have
we're
names
just gonna
either.
derive these one by one.
Yeah. And for your third one, what you're gonna do is the same thing except divided by sine squared.
When you divide it by these things, what happens to the graph?
This is not a graph right here.
Well, yeah, but when you put it on the triangle, what does it do?
Oh, so you're asking about like what happens on the unit circle?
Yeah.
I actually have a diagram of that right there on your paper.
Oh.
It's a very useful diagram, but it's basically a graphically representing all these tangent squared, secant squared, whatever. Okay? So if I were to simplify that, I'm just going to do it for the sake of time. And change my mind. It would be 1 plus cotangent squared theta. Do you remember what cotangent is?
Cotangent.
It's right here. Cotangent, cosine over sine, which is also equal to 1 over
tangent.
Exactly. Good. Just checking. Equals. Shoot, none of these work. Wow. Okay, so these are your three that you'll be using a lot. And these are useful because when you're given an expression or an equation that's kind of difficult to work with, you can use these to manipulate the equation. For example, if, for example, I told you to simplify, actually, let's just look at the homework. Okay, never mind, these are too hard. What can we do? So what if we had one minus cosine squared theta over sine theta? I want you to simplify this. Okay, so first thing I recognize is we can use this in correlation with that. Okay, so if we rearrange this identity and we subtract this from both sides, we get 1 minus cosine squared theta equals sine theta. All right, sine squared. Sorry. Okay, so we can replace this top bit with sine squared theta. Sine theta. Okay, and then this simplifies to sine theta. So this is how you would use all of these identities.
So you just rearrange them to like substitute them into whatever you're solving for.
Yes, you'd use these identities or these identities rearranged in some way to substitute like for things like that to make expressions or equations easier to solve. Okay, let's take a break because I need water. So, I'll be back.
Yeah, I know.
Did Harrison ever respond?
No.
Dang, what the heck?
You can always just hop on.
I know, right? Just take a field trip.
That would be kind of like
A little awkward.
yeah. Oh, it says he's active too.
Really?
Yeah.
Did he see your message?
No, I don't think he's. It doesn't show.
What the heck, Harrison? I don't know why Kristen's not here either.
There's something like we're missing out on, right? Like they use something we did about timing, you know?
I mean, I should have known, I guess.
Yeah.
None that I know of, I think. I hope.
Was it the same? Today's what, Friday? It was the same time last time on Friday, right?
Yeah.
I think the only change was Sunday, but no one at one time.
Yeah, but we were going to inform them of that today, so.
Yeah.
They should not even know about that.
No, I mean like for last week.
Oh, last week? Yeah, okay. I don't know what's going on. Do you want to continue now?
Sure.
Cool. Okay, so I'm just going to give you some practice problems. We can do the first one together. We're using these. Let's see. Okay. Tangent squared x over tangent squared x plus 1. Simplify this. And by simplify, I mean put it in like, if you can simplify it into sines and cosines, do it, as long as, well, I don't know how to explain this, but like simplest form means it has like the fewest operators possible. So for example, if you end up with 1 over cosine theta, you can simplify that into secant theta because that has one less operator, it doesn't have the division, right? So that's what I mean by simplify. So simplify this to its simplest form. Sorry, again, using these things. Or whatever stuff on your formulation.
A question about the identity formulas.
Uh-huh.
Does the theta represent an x?
Yes, theta can be replaced by whatever variable, yeah, or an angle measure. So like sine squared of 99 plus cosine squared of 99 equals 1. So theta just represents anything. As long as both of these are the same variable or same number, then this identity holds true.
Okay. I feel like a lot of steps to this.
There should not be. You want to walk through this together?
I mean, like, I think I simplified it, but I'm not sure.
What did
Like,
you
I
end up
got
with?
secant squared x over secant squared x plus 1. I mean, it wasn't really simplifying it, it just changed the 100, I guess.
I don't think that's right. So how did you, this cannot be, so notice that this is what your identity is. So you can't just replace tangent squared with secant squared, because secant squared equals tangent squared plus 1.
Yeah, but then you can do tan squared theta equals secant squared theta minus 1.
Right. So is that what you did up here?
Yeah, I just wrote it wrong. So.
Okay. So you should just recognize that this is the same as this part.
Yeah.
Okay. And just a hint, it's often, you can often simplify things a lot more if you convert them into sines and cosines.
Wait, but I can't convert into sine and cosine in this case, right?
Okay, what did you get?
Um,
What step after this? What did you do?
Secant squared x minus 1 over secant squared x.
Okay. So I think this just takes a little practice to kind of know how to manipulate this stuff, but I'm not going to touch the top because I don't have any like addition or subtraction, so it's already kind of nice because I can already convert it to sine or cosine. And I want to change this bottom one because this plus 1 is kind of bothering me. And if we can make this like not have any addition or subtraction, maybe we can convert both the top and bottom to cosines and sines, then we can cancel things out. So I'm just going to convert this bottom part to secant squared. Okay, so my next step is going to be tangent squared x over secant squared x. Okay, now I can convert both the top and the bottom to sines and cosines. And just a note, you don't have to have it like without, you don't have to take out all the addition subtraction in order to convert it to sines and cosines. When all else fails and you have no idea what to do, converting to sines and cosines is always a good way to start because then you can just try to simplify however way you can by multiplying.
But how do you simplify those two to cosines and sines if there is no like identity formula for it?
You can use your like the definition identities. Look at the very top of your sheet.
Okay.
Tangent is the same thing as sine x over cosine x, right?
Yeah.
And secant x is
secant x 1 over cosine x.
okay. So since this is secant squared x, I'm gonna make this cosine squared x, right? Look, we have a cosine squared x and we have a cosine squared x. How does this simplify?
Oh, so you just is sine squared x.
Exactly. Sine squared x. Okay, so It just takes a little practice to be able to manipulate things in the way you want to go, and just do some practice, I guess. That's all I can tell you. Okay, here's another one. I'm erasing all these, but you still can refer to your little sheet thing.
Sure.
And you can get help. Okay, I want to simplify this. And before we start, just a caution. The identities that we were working with all involved squares. So cosine squared theta plus sine squared theta was 1, right? This is not the same thing as cosine theta plus sine theta. They have to be squared. So don't look at this and think it's something else. Okay, so you want to walk through this together, or do you want to try it yourself?
I'll try this.
Okay, cool. I'll go get water, and I'll be back in a few minutes. How did you do?
Good. So do you want me to simplify it to the point where like it's just one term, or like to the point where like I have it to sines and cosines?
Simplify it as far as you possibly can.
I mean, like I could add everything, but I don't know if that counts as simplifying. Can I read you what I have so far?
Yeah, sure.
Sine squared y over cosine squared y plus cosine squared y over 1 plus sine squared y.
Say that again, let me write it down. Sine
Squared y over cosine squared y plus cosine squared y over 1 plus sine squared y.
How did you do that?
Well, first I squared everything. Like I made it tan squared y, or tan squared y.
Okay,
plus-
wait, we're not allowed to do that. So
Oh,
if you just square everything, that's not going to be equal to what it was originally. So if you have a number and you square it, now this is 1/4. That's not the same thing as half. So we can't just add squares to everything. We can't do that.
alright.
Okay, so that one's not allowed.
Okay, then I can change this.
Okay. I'll give you a hint. Did I write this down correctly? Yeah, I did. Okay. Should be fine.
Wait, what does the term you added just now?
My hint is to multiply this piece by 1 minus sine y over 1 minus sine y. Because this will make the denominator into 1 minus sine squared y, right?
Oh, I see.
Right? And then we can use one of our identities, convert that to something else.
Okay.
Have you gone anywhere?
Almost.
Okay. What do you have so far?
Hold on a second.
Okay. Okay, that's fine. Just take your time.
I've simplified everything to sines and causes.
Okay, so what do you have?
Sine y over cos y. Plus cos y times 1 minus sine y over 1 minus cos squared y.
Okay. So that's good. You converted everything to sines and cosines. So what do we know? Oops. Wait a minute. How did you end up with this? Did I copy this down right?
Yeah, I used to copy it.
So what did you?
Well,
What did you
sine squared y plus cosine squared y equals 1. So
Right.
then 1 minus sine squared y would equal 1 minus cosine squared y.
No, not really. Cosine squared, sine squared equals 1. So 1 minus sine squared equals cosine squared.
Yeah, so then we started with sine squared, right? Like 1
So
minus sine
when you
squared.
multiply this by that, then that'll be 1 minus sine squared, which is this. Right?
Yeah.
Or if you wanted to, let's say you were solving for, I think what you did was you just substituted something for sine, right? So if you did sine squared equals 1 minus cosine squared. Is that what we did?
Yeah.
So this denominator would be 1 minus sine squared y, right? Then you would just replace this in here. And then you would still end up with the same answer, because 1 minus cosine squared y. What is this? 1 minus cosine squared y.
1, so that's just cosine squared y.
Exactly. So your denominator here should be just cosine squared y. And I think that's where you made the mistake, and that's why you're stuck. So do you know what to do from here? Can you see anything you can do right off the bat?
I mean, there's nothing to cancel out.
There is.
That's cosine y.
Yeah, exactly. But remember that cosine squared y is the same thing as cosine y squared.
But you can't square the top side.
You can, but remember, like x over x squared, you can cancel out an x and I'll just put 1 over x.
Oh, okay.
We're doing the same sort of thing.
Alright.
Okay, so we can cancel this out, and this will become just cosine y.
Okay, I see.
Okay, and now we have the same denominator, right?
Mhm.
So you want to try from here?
Okay. So you got 1 over cosine y.
Which is equal to? We can simplify that, right?
What would I simplify it to? Like just more sines and causes?
No, there's a reciprocal function for 1 over cosine, right?
Oh, so R.
That's the inverse. It should be on your sheet.
Yeah, see.
Secant y, right? Is that what you got?
Yeah.
Cool, that's the correct answer. So this is pretty much you pretty much just need lots of practice to manipulate equations and recognize, oh, I can do this with this, I can do that with this. Yeah, so in general, when you have a denominator like we did in that problem where it was 1 plus sine y or something, what you can do is you can multiply it by the conjugate, so 1 minus whatever, and then that'll get you something squared, and then you can use one of the properties, one of the identities. Moving on. Okay, look on your sheet. There should be a bunch of equations that say sum or difference, right? So this is pretty much, there are derivations for this, but this is really, really long to do, so we're not going to go over that. Pretty much you just have to memorize, but you can do tons of things if you just remember the sum identity for sine and the sum identity for cosine. Okay? And the reason that is sine of A plus B equals sine A cosine B minus sine B cosine A. Right? It might have these slipped or something, depends how you want to write it. If you had A minus B instead of plus B, you can think of this as adding negative B, right? And then you would just replace all the B's with negative B, right? So using what we know about odd and even functions, cosine of negative B is what?
It would be 1 over
So
cosine.
since this is an even function, cosine of negative whatever is equal to cosine of the same.
Yeah.
So this is the same thing as sine A cosine B, right? And then sine of negative B, remember sine is an odd function. So sine of negative B is the same thing as a negative sine of B. Right. And since this is already a negative to begin with, if we add another negative to that, it would be positive. So that'll be sine A. And notice that this is exactly what your sheet says. So as long as you can remember this first one, you'll be fine. Okay, same goes for cosine, exactly the same thing. So these are pretty much just plug and chug, and they're very useful when you're given some angle. Let's say you're given an angle like sine of 195 degrees. Okay? And they want you to find an exact answer. In other words, you can't just plug this into a calculator and get a decimal. You can use this addition property, this identity thing, and split this angle into two angles that you like know for sure what the sine value is. So I'm going to split this into 150 degrees plus 45 degrees.
Okay.
Okay? And we know what sine of 150 is, and we know what sine of 45 is.
Through the unit
Yeah, the unit circle, exactly. Because the unit circle does all the 30-degree increments and all the 45-degree increments. So we know how to do this. And so pretty much you just plug and chug.
Gotcha.
Yeah. I'm not going to go too much into this because there's more difficult stuff we have to go over. But yes, this part is important. There's a lot of problems like this. I'm just not going very much into it because it's easy. So pretty much just look for two angles that you know the values of, and then you can do all that stuff. Okay. Double angle identities. It should also be on your sheet, but you really also don't need to memorize those because you can derive it from these. You can think of this as a plus a. If you had to find sine of 2a, that's the same thing as sine of a plus a, right? And then you just replace all these with a's. It's pretty easy. I did something wrong, didn't I?
Yeah.
Did I mix up the plus and minus? I probably just mixed up the plus and minus. I'll just like that. Right? Where's my sheet? There it is. Yeah, I mixed up the plus and minus. So yeah, and then this is become 2 sine A. Okay, so like I said, as long as you can remember the sum formula for sine of something plus something and cosine of something plus something, you're good for a lot of different things. So double angle identities, that's pretty much all you should know. And also notice that these can go backwards. So if you're given something like this, you can go backwards and get to that. So for example, if I say 2 sine x equals, I don't know, 3 or something, you can, let's make this better. Okay. You can convert this into sine of 2x. Sine of 2x is the same thing as 2 sine x cosine x. 2 sine x cosine x is the same thing as sine 2x. Okay? And then 3 over 2. And this is kind of skipping ahead, but we can solve this. This is fine. When you have an equation in trig, pretty much what you want to do is isolate it so you have like one trig function, which is kind of what we just did. And so by one trig function, I mean like not all different sines, cosines, tangents, but make it one type, right? And then you can solve it the same way we've been solving everything else. So we can treat this as like one variable. So 2x equals sine inverse of 2. And we know what this is, right? You can look at the unit circle.
Oh, 60.
Yep. 2x equals 60 degrees. X equals. So yeah, that's how you solve equations. We'll go over this more in depth in a few minutes. And just a few more things that you probably need to memorize. Unfortunately, these cannot be derived from this one, so you kind of just have to memorize it.
They're on this, right?
Yeah, they are on there. It's half angle identities. So sine of something, it's called theta over 2, is equal to plus or minus the square root of 1 minus cosine theta. Is this correct? I kind of don't remember these very well. Should be on your paper. It's on the back, I think. Yes, that's correct. Okay. And I'm going to explain this plus or minus first. So in your unit circle, over here, So sine refers to your y coordinate, right? So all the way this way on the circle, this top half, sine is positive, right? And all the way over here, sine is negative. And for cosine, you're referring to your x coordinate. So all over on this side, x is positive, and all over on that side, x is negative, right? The reason why we have to have a plus or minus for half angle identities is because, oh, why did I erase that? Oh, no, I need that symbol. Let's say your theta is somewhere over here, okay? So that means your angle is this thing right here, right? If you were to take sine of theta over 2, and you divide this angle by 2, your new one is going to be somewhere over there, right? And notice that the sine of this angle, sine of theta, is negative. But sine of theta over 2 is positive. And so when you're finding sine of whatever over 2, you have to decide whether it's going to be plus or it's going to be minus by drawing this thing and deciding the resulting angle divided by 2 is it going to be somewhere where sine is positive or is it going to be somewhere where sine is negative? And then you just decide to put plus or minus. In this case, if we use this angle, let's call it like 4 pi over 3, 4 pi over 3, or something. Then I would choose a positive because sine of half of that is going to be positive. Make sense?
Sort of.
Sort of?
Yeah.
So if I have a unit circle and I choose, let's say theta is here, that means that I went all the way around that way.
Okay.
Right? So sine of half of this angle would be somewhere over here. Or, no, let's go there. Somewhere over there, right? So sine would be positive or negative.
It would be positive.
Exactly. Okay? So that's what this plus or minus means. And then after that, it's just plugging and chugging. And notice that this is cosine of theta, not theta over 2. So if I gave you a problem like find sine of 22.5 degrees, okay? This is the same thing as sine of 45 over 2, right? So we find is it plus or minus. So if we have angle 45 and we take half of that, right here, is sine positive or negative?
Positive.
Right. Okay, so we take positive, and then 1 minus cosine of 45 over 2. And then plug together.
Question.
Mhm.
Couldn't you just like convert degrees into radians and then solve it that way?
You mean this thing?
Oh,
Well, you still wouldn't really know because this is pi over 8. If you're given pi over 8,
oh, is that what that is? Okay.
yeah. And this is pi over 2. 45 is pi over 2. I mean, pi over 4, sorry. So it's the same thing as pi over 4 over 2, which is pi over 8. So you'd still have to do the same thing.
Okay.
Okay, so that's how you do those. Once again, just plug and chug. Not going to go very in depth because it's pretty easy. Okay, now we're going to get more into the equation sort of thing in the last 10 minutes. Let me just check that I went over everything I need. Cosine, sine. Ooh, okay. Yep. Okay. So when we have equations with trig, we're going to solve it just like we solve any other equation by solving for, I'll just give an example, cosine of theta equals root 3 minus cosine theta. Okay, we're going to try to isolate the trig functions as much as we can. Kind of like when you're solving for an absolute value, you isolate the absolute value as much as you can. We're doing the same thing. So I'm going to add cosine theta to both sides to get rid of this. So I'll end up with 2 cosine theta equals root 3, and then divide it by 2. Cosine theta equals root 3 over 2. And now we know what to do with this, right?
Yeah.
This is something we recognize. So
That's 6.
yeah. No.
No?
No. We're looking at the x coordinate, not the y
Oh,
coordinate.
X coordinate. So then, 45.
No. Almost. You get x coordinates here. Can you see it? But it's here, but
is
that one is
okay.
really like, yeah, so it's okay. Or pi 6. Our answer is not quite finished here because on our unit circle, remember coterminal angles? So yes, at pi over 6, cosine of pi over 6 equals that. But also we could go all the way around the circle again, and it'd still be pi over, like the answer would still be root 3 over 2, right? So essentially we have this plus any, like you can rotate however many times you want as long as it ends on this, right? So what we're going to do is we're going to add 2 pi n, where n is any integer you want. So it can be -1, it can be positive 100, because 2 pi is one rotation, right? So if we add 2 pi, it doesn't matter how many times, n times, as long as we end on pi over 6, you'll get that number. So your answer will be this. And this is only if your instructions are just to solve for theta. Sometimes it'll say solve for theta if theta is between 0 and 2 pi. So that means just within the first rotation. And then you wouldn't need this plus pi n. But unless they say that, you do need to include it. Okay? And if you use degrees, then how many degrees is one rotation?
Like, it would just be a full 39, 60.
Exactly. So this would be 30 degrees plus 360 n degrees. Got it? Cool. So, next one. You can do the same thing with quadratics. So if you have sine squared theta minus 2 sine theta minus 3 equals 0. Notice that we have a sine squared and we have a sine. So we can treat this as kind of a quadratic function. For now, to keep things a little more clear, I'm going to replace sine theta with some other variable. I'm going to call it a. Okay? So a squared, right, sine squared theta, so a squared, minus 2a minus 3 equals 0. This is something we know what to do with, right?
Yeah.
How do we solve this? We can factor, right? So how does this factor?
A plus 1, or a plus 2, and then a minus 1. Right? A plus 3, a minus 1. Or did I mix up the pluses?
You mixed, yeah, you mixed it up.
Okay, so a minus 3, and a plus 1.
Cool. Okay, and equals 0. So we know a equals -1 or a equals 3, right? This is, okay, we can use this example, it's fine. So now I'm going to go back and replace all my sine thetas into a. So we know sine theta is -1 or sine theta equals 3. Does this make sense?
Yeah.
How we got from here to there?
Yes.
And now we know what to do with these, right?
What?
We can use sine inverse and just find what's
Oh,
this
okay.
angle, right?
Yeah.
Okay, so what angle will make sine of that angle equal to -1?
So I'm looking for the x coordinate.
Y
How
coordinate.
do you know?
What do you mean?
Like,
How do you know?
whether you're looking for x or y coordinate?
Because sine always corresponds to y. Cosine cosine always corresponds to x. Sine always corresponds to y.
Okay. So then it's x in this case. Y.
It's y.
Yeah.
Yes.
Okay. So -1.
The radius of the circle is 1.
Okay. So 3 pi over 2.
Yes, exactly. So theta equals 3 pi over 2. And what do we have to add to this?
Minus 2.
Or 2 pi m theta, right?
2. Oh.
Remember, because we can go however many rotations.
Yeah. So plus 2. Okay.
Exactly. So this is your answer.
So you add the rotations to the thing, like to everything, basically, right?
Unless it tells you that you're only looking for an answer between 0 and 2 pi. Then you wouldn't have to add this 2 pi n.
Mm-hmm.
But if it doesn't tell you that, and it's just saying, what is theta? Well, there's infinite answers for theta. It can be anything because it repeats.
Okay.
So now for this one,
same thing, right? Except like the other.
Right, so it's the same process. You're taking sine, it's the same thing as going like theta equals sine times the 3. But in this case, you can't do that because remember sine theta is always between -1 and 1. It can't go beyond that. It's always between -1 and 1. So this one is just no solution. No solution. So this is your only answer.
Okay.
This is just something to be careful with. Oftentimes you will get no solution. And yeah. Okay. Next example. We're almost out of time. Just one more and I'll go over. Sometimes in equations like this, not all of them will be in the same type of trig thing. So sometimes you'll have something like cosine squared, let's call it x, equals sine x plus 1. The first thing we always want to do is convert all of these to just one type of trig function so that we can do something with it, right? So I'm going to use one of the identities, the Pythagorean identities that we learned about, to convert the cosine to a sine.
Yeah.
And I know that cosine squared theta is the same thing as 1 minus sine squared theta, right?
Yeah.
Do you agree with this?
Yes.
Okay, so this equals sine x plus 1. And now we have a sine squared and we have a sine. What does this look like?
You can quantify.
Exactly. So I'm just going to move everything over to one side. 0 equals sine squared x plus sine x. Yeah? Now we can factor sine x times sine x plus 1.
Yes.
Okay, this sine x equals 0, or sine x plus 1 equals 0.
So only the right one would work, right?
This one would also work, because sine x can equal 0, it just can't be beyond -1 or 1.
Oh, okay, beyond.
Yeah. Okay, so what's the answer to this one?
90.
So we're looking at y. When is y equal to 0?
Oh, 0, okay. So, 270.
270 is in here. When is y equal to 0? So we're looking at when is it equal to 7?
Right. So 180.
180 and also at 0 or 2 pi, right? So your answer could be just 0 plus 2 pi n, or it could be pi plus 2 pi n. But in this special case, since it crosses at 2 different points and there's 180 degrees between either of them, you can just say pi n because this is pi, right? So as long as you end up along like either of these ends, it's fine. So your answer would be simply pi n. Okay? And then how do you do this one? Sine of x equals, okay, and x equals, we just did this one.
So 2 pi over 2.
Yes. And is that your final answer?
No. Plus 2. So it's 2 pi.
Exactly. Perfect. Good. Okay. So what if this was cosine of 2x and 2x? And change, imagine it's changed through the whole thing. I don't have time to change it. But after we got to the end, we got to sine of 2x and sine of 2x plus 1. Okay? How would we do this? I'm going to walk you through this because there's not much time left.
Yeah.
Okay, so same thing. I'm just going to treat this as some angle. Okay? It's not like two different things. It's just some angle. So this some angle, whatever this angle is going to be whatever you just found, right? So it could be 0 plus 2 pi n, or it's pi plus 2 pi n. And both of these, if you just combine it, this becomes pi n, right? Only after you've reached this almost final answer, like you've already added your 2 pi n's and whatever, then you divide by 2, and you divide by 2 to solve for x. And this becomes pi over 2. Okay? You don't divide by 2 before adding this. You divide by 2 after you've done everything. Okay? And for this one, how did you do this? Sine of 2x is 1. 2x equals,
Oh, okay.
yeah, oh, yeah.
I see.
You can't just,
Yeah.
3 pi over 2 plus 2 pi n, right?
Mhm.
And then you can divide everything by 2. Not before you add this. You have to add this first before you divide by 2. Okay, so this would be 3 pi over 4 plus pi n. Okay, that is all for today. It is 4:04. We are done.
Okay.
Okay, I'm not really sure what's going on with class on Sunday, so just check your email, your phone, or your parents, whatever stuff.
And the
stay
final
updated.
is Monday?
Yes, final will be reviewed on Monday. And you already got it, right?
Yeah.
Cool. Okay.
Okay.
Unlimited time, and you can use the sheet.
Oh, it's just 120 minutes here.